All right, so in this video, we're going to be going over how to calculate equilibrium concentrations. If you're given a K value, we can actually figure out what are going to be our concentrations at equilibrium if we know how much of a reactant or a product we put in initially. So let's say we have this chemical reaction. If we put in an initial concentration of 0.850 of our reactant, and 0 concentration of our product, which is typical, right? We just put in reactants. We can think about the change in concentration. Now, the change in concentration is basically telling me what direction is the reaction going to go. If I put in only reactant and I have 0 products, what direction do you think the reaction can go? It can move to the right. If I move the reaction to the right, that means I'm going to be using my reactant, so we'll say negative for my change. And I'm going to be creating products, so we'll say positive for our change. We don't know exactly what the change is, though, so we'll just use X. Then the equilibrium concentration is going to be whatever we started with plus the change. So we can use what's called an ICE table, I, C, E. And I plus C equals E. So you can think about it as being like an old school addition problem, where I can take the I row plus the C row to equal the E row. And the E row, this is what goes in the equilibrium expression. So you can imagine what we can do now if we have our equilibrium constant, and we can maybe figure out what equilibrium expression is, and then we can plug in some values and try to solve for X to see what our equilibrium concentrations will be. So our equilibrium expression would be products over reactant, and we know the value of that, and then we know our products and our reactants at equilibrium, and so we can just plug that in. If we solve for X, we get this value. But X, remember, is just the change. It's not just the answer necessarily. So we have to apply the X now to the answer. So how much of the product did I make? Well, the amount of product I make was X. So it's just the amount of product is X. But the amount of reactant is what I started with minus X. So it'll be whatever I started with minus whatever I have solved for X to get a new value. So I hope that makes sense, just looking at this very, very simple example. Let's look at another example. Why don't you at least try to get it set up, and I'll walk you through it. But if you want to try to pause and get it set up, go ahead. Okay, so we're going to start with our ICE table. You may hear some people call it rice table because we put a reaction on top of it as well. So we have our initial, our change, and our equilibrium. Tell me the K is 54.3. Let's go ahead and write our equilibrium expression. I feel like a lot of students forget to do this at the beginning and then they get a little stuck at the end. So go ahead and write the equilibrium expression. I know what this equilibrium expression is, so I can write it out. It's going to help me in calculations later if I just have that set off to the side. And we know that value is going to be 53.4 at that certain temperature. I don't need to use the temperature in any calculation right now, but we know that K can change with temperature. So we're usually given the temperature. What will the concentrations be at equilibrium? So I'm asking you, what is going to be here in the E part at the end? I want numbers. If I started with 0.240 molarity for both my reactants, if it doesn't tell me anything about products, that means I have 0 products. If we have 0 products, what way is the reaction going to go? It's going to go to the right because I don't have any products, so I got to make products. If the reaction goes to the right, we're going to subtract our reactants and we're going to make our products. Now, one quick thing here. Look at the ratios. For every one H2 I lose, how many HIs do I make? 2. For every one I2 I lose, how many HIs do I make? 2. So we're going to always take the coefficient. We're going to say, hey, we're going to make twice as much product as we remove reactant. So we're going to take that coefficient and we're going to pull that number into that change area of the table. And then remember, I plus C equals E. So I'm just going to add up. I drop the unit here just for ease. And now I have my E. What we have for E, well, that gets plugged in to our K expression. But at any point you want to pause and work it out on your own, go for it. So we know our K is 54.3, and I know my HI is going to be 2x, and I know it's squared. Divided by 0.240 minus x times 0.240 minus x. Now you may be thinking, oh no, I'm going to have to FOIL out that bottom, and then I'm going to have quadratic formula. Well, let's take a look first before we get too upset about solving for x. Can I not rewrite this like this? If both the top and the bottom are squared, now to solve for x, all I have to do is take the square root of both sides. So I can take the square root of 54.3, and that would equal 2x over 0.24 minus x. And now it becomes a lot easier to solve. So one way to avoid doing the quadratic formula and doing a whole bunch of extra math is just to see, do I have a situation where both the top and the bottom can be squares, and I can just take the square root of both the number for k and the fraction. As we do this algebra out, we'll find that we get an x is equal to 0.189. If you need help with that algebra, definitely let me know. But this is not quite our final answer because I want to know what is the equilibrium amounts for each. So the amount of H2 at equilibrium would be 0.240 minus x. And this would also count for the I2. So that would give us 0.051. And again, concentration is molarity, so let's throw that unit back on there. And then for HI, it's going to be 2 times x. 0.378. And again, we'll give the molarity for that one. So I know it looks difficult, but the ICE table was really there just to help us organize information, which you know is the big thing that a lot of us need to work on to make sure that we're solving problems correctly. So why don't you try this one? Same reaction that we worked, but now we have initial concentrations for all 3 things. See if you can figure out what might be a little bit different here. Okay, so hopefully you paused and you tried to get it set up. So let's set up our ICE table. Same reaction as before. However, now I don't have a clear direction of where I'm going. Because I have amounts of all 3 things. So what direction is this reaction going? Is it going to the right? Is it going to the left? Well, we can find our Q. Q is going to be products over reactants, just like K, but it's at any point in time. So we can plug in our values. to get a Q. And then we can compare it to K. So we go back up to the first one. They gave us K up here for the same reaction as 54.3. So when we calculate this, our Q is 69.7. Q is greater than K. So that means we have too many products or not enough products. Too many products. So too many products means the reaction is going in reverse. If the reaction is going in reverse, we're going to subtract our products and we're going to be making reactants. Notice that I brought that 2 down into my change row. Because we're going to be, it'll be 2 times as many HIs as the other reactants. Now, again, we're just going to add up I plus C equals E. And then we'll take our E and we'll plug it in. So we know K is equal to 54.3, which is now going to be equal to 0.0424 minus 2x squared over 0.00623 plus x, 0.0414 plus x. Now this one, I unfortunately don't have a trick for you because K is very not a small number. There's a trick I'll show you in class where if K is a small number that we can kind of exclude the changes. For this one, it's not so. So work this algebra out. You will have to do quadratic to solve for x. Work it out to your best ability. And the answer that you should get for x, and this is showing you kind of all the work out here. So if you can look at these steps to see if we're kind of going wrong with it. So we get 2 versions for x. Well, concentration can't be negative, right? So if we have like an x, let's say the x is an amount of substance we're losing or we're making, can't be negative. So we would get rid of that one. And so then we would plug in those x values to the rest of this to get our final answers. So stretch your algebra muscles and try the quadratic out. But that's what you should get for that x there. Okay, this is all for the video. We're gonna do some more practice in class.